Hello everyone. This morning, this moment, I want to share you again regarding how to solve some question about thermal physics. Yeah, this is for CIA Cambridge. Yeah, uh, but before we continue, don't forget to subscribe this channel. Yeah. Okay, let me start. Number one. The equation of state of an ideal gas is PV equals to nRT. For each, the symbols state the physical quantity and the SI unit. Okay, symbol P, V, N, R, and T. Yeah, P. Yes, P is actually pressure. Yeah, this is pressure. Then the unit is Pascal uh, or Newton meter square ya, Newton meter square. Then volume, ya, V is volume. Ya. Volume is in meter cubic, and N, yeah, small n is number of moles. Yeah, yes, number of moles. Yeah. P is pressure, V is volume, and N is number of mole. The unit of moles is mole. Yeah. Then R is constant number or molar constant number. Yes, molar constant number. The unit is joule over kilogram over mole. Yeah. Joule kilogram mole. Yeah. And what about T? T is temperature. Yes. Yeah. Temperature is in Kelvin ya. Temperature is in Kelvin. Yes. Yes. Okay. P is pressure, unit in Pascal or Newton meter square. And then volume is meter cubic V. Yeah. N is mole, uh, number of moles. And R is constant number, but molar constant number. And temperature T is in Kelvin. Yeah. Okay, we continue to the B question. Yeah. On the B question, an ideal gas of volume 1.0 times 10 power minus 3 meter cubic is trapped by a piston in a cylinder as shown in the diagram. There is negligible friction between the piston and cylinder. Initially, the temperature of gas is 20 degrees Celsius. And the external atmospheric pressure acting on the piston is 100 kilopascal. Yeah. Okay, we see the cylinder. This is heater, cylinder, piston, and trap gas. The gas expands slowly when heat is supplied the electric heater inside the cylinder. Yeah. Okay, question I. Yeah. Calculate the work done by gas when its volume slowly increases by 5 times 10 power minus 5 meter cubic, yeah, at a constant pressure. Okay, work done, yeah, or P delta V. Work done is P, yeah, V2 minus V1, yeah, delta V, yeah. Work done is P delta V, yeah, or P times with V2 minus V1. Yeah. So P is constant at number P is this, yeah, 100 kilopascal or 10 power 5, yeah, uh, Pascal, and times with this is increased from uh, 1 times 10 power minus 4 to 5. Okay, uh, if we see this is, yes, 1, 10 power minus 4 minus 0.5 actually, yeah, 10 power minus 4. Yes, a half times, yeah, yeah, actually this is 5, yeah, 5 joule. Yes, the work done is 5.0 joule, yeah. Okay, other question, what is the temperature of gas in degrees Celsius following its expansion? um we say about the uh, relationship or between V and T, V1, T1, yeah, this is something with V2 divided by T2. Okay, when we see about volume 1 is we use this here, this about 10 power 4 here. This is 10 power minus 4 divided by temperature. The first temperature is 20, yeah, 20, yeah, 20 we change into Kelvin. This is something 293, and then volume 2 is 1.5 times 10 power minus 4, yeah, yes. And if we will find about T2, yeah, T2, yeah, actually 1.4 times 293, yeah, T2 something with 293 times with 1.5, yeah, yes, this is around 440, yeah, Kelvin. Yes, that's the answer for number question I. How about question I3? Yeah. Describe two things that occur in motion, the typical molecule of the gas, yeah, during the expansion. Yeah. Uh, any two form of uh, the following. Yeah. The first one is this is about speed, or kinetic energy, increases. Also, let's say collision rate. Collision rate. Yeah, with walls. With wall. It decreases. Or time between collision increase. Mm, Other condition also. This is about distance. Distance. uh, Distance between collision. Sorry, distance between collision increases. That's mean. Free path inverse. Proportional to molecule density. And inverse proportional to molecule density. Yes, I think this is the best answer for three. Three things that occur motion of the typical molecule of the gas during the expansion. Okay, we try continue number two. Yeah. Don't forget to subscribe. Please click the button of uh, subscribe. Number two, state the equation of state for an ideal gas. Of course, about PV and RT. This is PV and RT. Okay. See number B. Oh. A fixed mass of an ideal gas is heated while its volume is kept constant. Sketch a graph of the axis below the show how to pressure P of the gas varies with the absolute temperature T of the gas. Hmm. Yeah, this is straight line and through the origin. Uh, the graph must be straight line. Straight line and uh, oh sorry, oh through the origin. Hmm. what mean is, yeah, this, if we draw the line, yeah, draw from the origin and then strike line, yeah. Okay, now question C. Explain intermolecular motion why the pressure of the gas in part B varies with absolute temperature. You may be awarded mark from the quality of written communication in your answer. Okay, uh, this is the first one is about average kinetic. Yeah. Okay. Average kinetic energy or speed of the molecule increases. Speed of the molecule increases with with temperature. Uh, other other condition is more collision, more collision occur, or let's say this is more frequently. Mm, or more particle hit per second. Let's say this is more particle uh, particles, sorry, hit per second. Okay, let's say all the condition is average. This is about average of change in momentum during a collision is greater or rate of change momentum is greater. Okay, yes, hence mm, force or pressure of moment during collision is greater. Yes, I think this is the best some answer. Okay, continue the question. Calculate the average kinetic energy of the gas molecule at a temperature 300 Kelvin. Oh, on 300 Kelvin, just we go to the kinetic energy formula. kinetic energy as 3 over 2 kT. So kinetic energy equals yes 3 over 2 k as 1.38 ya, Boltzmann constant times 10 power uh, minus 23 ya, and times temperature is in Kelvin is 300. So after we calculate around 3.74, yeah, 3.74 times 10 power 3 joules, yeah, or yeah, uh, 340 joule. Okay, this is kinetic energy of the molecule when the molecule has temperature of 300 Kelvin. Yeah. Okay, now number 3. Yeah. The diagram shows an arrangement that is used to measure the density of powder. The air is the cylinder of force into the flash, and the air pressure is measured by pressure gauge P before and after the change. Yeah. The test is then repeated with the powder present of the flash. In both tests, yeah, the initial pressure in the flash is the same. Okay, pressure gauge, piston, cylinder, and flash. Yes. Explain why. Yeah. Explain why after compression of the air, the pressure in the flash is greater when the powder is present when it's not present. Um, you may be a red mark of the quality written communication in your answer. Okay. Because yeah, this is when volume of air, yeah, when volume of air mm, is less with the powder present. Okay. Also, pressure, yeah, uh, inverse proportional with volume. Yeah, this is inverse proportion, proportion, yeah, with volume. So, pressure is greater. Yeah, because volume is less. Yeah, volume of the air is less. Okay, three question. I two. Yeah, calculate the pressure in the flash after compression at constant temperature, yeah, when no powder was present. Yeah. Assume that the volume of tubes and pressure gauge is negligible. Yeah. Okay, we have volume of empty flash 2.5, volume of cylinder 1. Okay, initial pressure of the air flash cylinder is 100 kilopascal. Okay. We will use formula of final pressure is uh, wait, oh, oh, Okay, we only use the perbanding ratio, yeah, final pressure. We use the formula of P1, P2, V1, V2, yeah. Or we can say final pressure is uh, as the initial pressure, yeah. Use the formula. This is P1 pressure 1 volume 1 equals to uh, pressure 2 volume 2, yeah, Boyle equation. So if we use P1, yeah, as the P1 is 100 kilopascal, yeah, something with 10 power 5, yeah. Volume 1 is 2.5, yeah, 2.5, 2.5 times 10 power minus 4, yeah, equals to P2 final pressure, yeah, and then V2 equals to, yes, this, yeah, 1 times 10 power 4, yeah, same thing with this number actually, yeah, copy, there, yeah, we can see here P2 equals to 2.5 times power uh, we, oh my god, oh, I mistake something, yeah, this is 3.5, yeah, because after, jadi 1 plus is 3.5 3.5 or 2.5 plus 1.0, yeah. Okay, so we have P2, yeah. This is 2.5, so, oh my god. Yes, yeah, yes. So calculate this number, uh, 3 over 5, 3.5 divided by 2, 1 over 4, yeah. Oh yes, 1 over 4 times 10 power 5, yeah, Pascal. Yes, or this is same thing with 140 kilopascal. Yeah. Okay, continue to be question. Yeah. To test the apparatus, 0.13 kilogram of powder of density 2,700 kilogram meter cubic was placed in the flash before compression. Calculate the volume of amount of powder. Okay. Volume of powder, yeah. Oh, I know. This is about density. Yes. We know about density has formula. Yeah. Yeah. Density as the mass over volume. Yeah. So if we find the volume, yeah, volume, yeah, V, yes, this is about mass over density. Uh, so mass is 0.13 divided by density 270. So Yes, around 4.8 times 10 power 5, yeah. 4.8 minus 5, yeah, meter cubic, yeah. Yes, this is the volume of the powder. Yeah. Question II, yeah. Okay. The pressure of the air in the flash increases to 150 kilopascal when the test was carried out with the amount of powder in the flash. By carrying out an appropriate calculation, justify, yeah, whether or not the test was successful. Okay. Uh, no. Let's say a summing. Yeah. Uh, summing what? Summing of powder. Yeah. Yeah. Summing of powder volume. Powder volume is as in on the BI, yeah, on the question that we have initial velocity, yeah, sorry, initial volume, oh yeah, sorry, as volume is wait, oh, 3.5 minus 0.48, yeah. Yeah, in uh, times 10 power minus 4, yeah, in meter cubic, yeah, in meter cubic. This is in meter cubic. So when final, yeah, final volume as 2.5, yeah, minus 0.48, yeah, same with that's, yeah, times minus 4, also in meter cubic. So we get the final pressure, yeah, final pressure as the uh, use the formula of PV, yeah. Mm, final pressure, that's same thing with 100 kilopascal, yeah, oh sorry, that times 3, yeah, and divide it, yeah, to, yeah, yes, we have 150 kilopascal. Oh, hmm. Yeah, it means, yeah, uh, that's successful as the calculate final pressure, yeah. same thing with measure final result. Yes. Okay. You see number 4 first. Yeah. I think one number again, number 4, and then you can continue with number 5 and so on. Yeah. This is just about example. Yeah. Okay, number 4, the number of molecules in 1 cubic meter of air decreases as altitude increases. The table shows how the pressure and temperature of air compare at sea level and at one altitude of 10,000 meter. Yeah. Okay, this is the table or information. Yeah, when on the sea level they have a pressure as a times 1 times the power 5 Pascal. The temperature is 300 Kelvin and the altitude 10,000 meter. Yeah, the pressure increases to 2.2 times 10 power 4. Oh, sorry, decreases. Yeah, and when the temperature is 270 Kelvin. Okay, calculate the number mole of air in cubic meter, yeah, of the air at sea level. Okay, this is about use the formula ideal case, yeah, n equals to b over rt, yeah. So yes, p is 1.0 times 10 power 5, yeah, or 10 power 5 uh, times with 1, yeah, because volume is 1 meter, yeah, per meter cubic, yeah, this is 1, and divided by 8.31, yeah, this is about gas constant, yeah, and times with 300, yeah, this is temperature, and we calculate this number. Wait, yes, around 40 moles. Okay, this is on the sea level. The second one is on the 100, sorry, 10,000 meter. Yeah, I think same thing with use this formula, yeah, but different in pressure and temperature. Okay, n equals to PV RT. So P is 2.2 times 10 power 4. And then volume is still 1, yeah. And divided by R is 8.31 and temperature is 270 Kelvin. Yeah, we calculate first. Okay, this is around 9.8 mole. Yeah. Okay, that's the A question. Yeah, so B question, in air 23% of the molecules are oxygen molecules. Calculate the number of extra oxygen molecules there are per cubic meter at sea level compared with cubic meter on the air in the altitude of 10,000 meter. Okay, this is we see about the first one is about total uh, Yes. For the total, yeah, total first. When we have 40 moles, yeah, and times with Avogadro number 6 point, yeah, 6 times 10 power 23. Yeah, this is around 1.8 uh, power 25 particle. And then we sorry, we still uh sorry, it's not correct, yeah. Minus also because on the altitude, yeah, of 10,000 meter we have 6 and 9.8 moles, yeah, times again about Avogadro number. Yes, so yeah, like this one, yeah. Yes, this is around 1.8, yeah, 1.8 times 10 power 25 particle. So oxygen molecules, yeah, this is same thing. Allow a CE for incorrect value and for A. Yes, because 23%. So oxygen molecules, yeah, yeah. Uh, Oxygen molecule 23%. Same thing with 0.23. Yeah, as well. 0.23. Yeah, times with that number. Yeah, 1.8 times 10 power 20. We have number around 0.23 times with 1.8, 0.414, yeah, or around 4.14, 4.14 times 10 power 24. Yes. Okay, I think enough for this session for explanation about how to solve some question in physics thermal. Yeah. Thank you very much for watching my video. Don't forget to subscribe this channel, like, comment, also share to the other. Thank you very much. Bye.